Many people see huge difference in hacking and using Metasploit or other automated exploitation tools. Still, these tools pave the way to quick and easy system analysis. Yesterday and today, we have heard talks concerning software and hardware vulnerabilities. Hardsploit wants to make it easier to look and analyze those vulnerabilities with your devices. Sometimes it is just about having the right tool. Here now to present the right tool are Julian and Gwendolyn.
Thank you. Thank you very much. Good evening, everyone. You are a lot. That's an amazing surprise for us. So I'm a little stressed, of course. So let's get started. With this presentation of Hardsploit, we intend to show you the goal behind the project, the goal we want to reach, and how we are going to reach it. We will end the presentation with a live demo of the tool. We like to live dangerously. So before starting, a quick introduction about us. So I'm Gwendolyn. I'm a pen tester and a software developer, among other things. And therefore, I'm in charge of the high-layer level parts of the Hardsploit development, like the graphical interface. And of course, I do love hardware hacking, and that's why I'm working on this project with Julien.
I'm Julien Mona, and electronic engineer, and I'm software pen tester and hardware pen tester, of course. And I'm a DIY enthusiast guy, because it's not expensive and it works perfectly. And for Hardsploit project, I'm the low-level developer, and I create the board and develop all the code for microcontroller and VHDL for the FPGA module. You understand what's FPGA after.
Okay, so the Hardsploit project is based on a simple fact that is the following. The gap between hardware and software security widened since the 2000s. I think we can't really argue with that because we read and hear a lot more about software stuff being broken and fixed every day rather than hardware itself. And we think that it's because mainly the hardware is a way to get access to the software. And, yeah, okay, sorry. So, the hardware is more a way to get access to the software. And that's very important for what's going on right now. I'm sure you've read a lot about the Internet of Things until you get fed up with it. These things that we are talking about are hardware products, hardware stuff, going from the simple smart T-shirt to the smart thermometer that is going to regulate the temperature of critical devices. Don't ask me why you have to add the word smart before everything related to IoT things, I don't know. And so just to say that it's not only about computer anymore. And the question we ask ourselves is, security speaking, is hardware the new software? We will have in our hands a lot of products, a lot of electronic products, able to connect itself to a network, and we need to assess their security. And to assess the security of the software part, we have made a lot of progress. We have great products, we have great services, great tools, and if you try to compare it to the hardware part, you can see that we have very few unimplemented solutions. And so we think that it comes from a lack of awareness from the designers. For the little example, one of our clients was wondering, reading the audit report of his product, how do you guys manage to get my firmware? And the answer was really simple. We use the same way you use to put your firmware in.
Yes, it's true. Yeah.
So quick and dirty procedure for hardware hacking. Let's imagine you have a thing in front of you, an object, an electronic product, and you want the potential data that can be stored in it. So the first step, of course, is trying to open the product. So some designers try to protect this step by making the product really difficult to open. So of course, it's not the best solution, because if someone really wants to open the product, he will be able to do it. He will not just be able to rebuild it and make it work again. Step number 2, fingerprinting. So when you have your product open, you will find a PCB, probably, with a lot of components, electronic components. And you just have to read all the references over this component and to find the interesting one. And this step is the read the fucking datasheet step. And when you have detected the interesting components, like memories or microcontroller, you are going to use them. So you have 2 ways to do that. You can unsolder the component and try to plug it on another PCB to work on it more easily. Or you can directly connect the tool you use to the component to perform an online analysis, so both ways. And then when you are connected to it, you try to perform read and write operation to access the data. And when, of course, you have the data, you are going to reverse engineering the process to try to find vulnerabilities and to exploit them, of course. This is our purpose, Hardsploit purpose. It's to dump all the data. We want to do that. But beyond that, we want to make this step number 4 right here to be a child's play, okay? And we want to dump all the data, allowing someone that is just able to read a data sheet or to solder 1 or 2 wires to do that, to dump the data.
So the goal is to create a bridge between the hardware and the software. Most of the time, a software pen tester know how to access the software, but when you have hardware, it's more complicated sometimes. So the goal today is just to present you a tool to create a bridge, to have a simple way to read the same data as a software pen tester have.
I told you before that my profile was more about software stuff. And a guy like me should be able, and now I'm able to do it, to interact with electronic components without having to struggle with a lot of documentation and things like that, and to know all you need to know about electronics to do that. Why? Why would you want to dump data? Okay, that's a bit of a silly question. But because, of course, you can find a lot of interesting information inside memories, inside microcontroller. You can find passwords in clear text sometimes. It's the equivalent of the sticky note on the screen of the computer or under the keyboard, but for hardware. You can find file systems and firmware. And yeah, maybe you're just a curious person and you just want to know how the electronic product you just bought works. It can be just that. And you should be able to do that. And so, how do you get access, how do you interact with an electronic component? You are going to use buses. So here is a not exhaustive list of them. We can find the SPI, I2C, JTAG. So you may be familiar with these buses. And so the more buses Hardsploit can handle, and the more we will be able to interact with electronic components. And this is our goal. So you may wonder, okay, but I know some tools that exist, and they do the same. They're the same as Hardsploit. And some people ask us this question a lot of time, so we just create a quick review of the existing tool. So like BuzzPirate or JTagulator, GoodFet, our tool, we are using them for our audit. But because we use them, we know what are their limits. And we took inspiration from them for Hardsploit. So you can see that, for example, we are the Hardsploit manage the parallel bus, so the parallel memories, and we focus mainly on modularity. All the tools are based on microcontroller, and we use FPGA that can be coded with VHDL to improve modularity. If a new bus came out, it can work with Hardsploit. Okay. So here is a little communication slide. How Hardsploit, how you interact with Hardsploit. How do you use the tool? We start first with the higher level, the GUI, so the graphical interface that is developed with Ruby programming language. So the interface communicate with the API. Hardsploit is connected to the computer with USB 2.0 communication. And then Hardsploit uses his microcontroller as a bridge to communicate with the FPGA and the FPGA memory by using the SPI bus. And then the FPGA, that's the big part. It's this component that is going to manage all the bus we can work with. And so the FPGA, with the compatible bus, will be able to interact with the GPIOs of Hardsploit in order to communicate with a target. So you can see a quick list of possible interaction, like sniffing, reading, writing, and executing custom commands.
And what you want, if you create a custom module in FPGA, you can send another one, and you can interact or create something like, I don't know, what you want.
If you know about VHDL, you will be able to create your own Hardsploit module to work with a specific bus.
Yeah, for custom protocol, for example, or something like that.
Okay, the prototype making. So we are a little company, so we use low budget style solution. We just buy for our first prototype. We just buy the PCB. And here you can see, yes, you're not dreaming, it's duct tape and PCB scrap to hold the board. It's the way we use to apply soldering paste on the PCB.
So, and for that we use a stencil, and when you put the solder paste through the hole, the solder paste put on the top of the PCB, on the top of the board. And after, you need just to put your microcontroller or FPGA or 64 LED manually, for example, and you can create your own board like that.
And this operation requires a lot of accuracy because the FPGA, for example, have like 64 pins, yeah. And they are really close to each other.
No, 144.
Oh, okay, sorry for that. And so, step number 2, you've placed your component with your little hands on the board, on the soldering paste. You use this slightly modified oven to melt the soldering paste. So it's a classic oven, of course, slightly modified with an appliance that Julian developed.
Yeah, it's not perfect. But it works.
You have to open to
lower the temperature.
But
for the last step, you need to open the door to decrease the temperature.
He told you DIY.
Yes, I'm DIY enthusiast.
And so, okay, the reflow one, and this is the V0.1 Hardsploit prototype. Okay, don't leave the room now. It's just only a prototype. Okay, we called it the Green Goblin. So huge baby, as you can see. So we have the 64 GPIOs at the bottom, the FPGA in the center. And Christmas Day, okay, day passed, and Julian improved the process. And so we gain a budget. And with this budget, we were able to buy some more efficient tool. So the stencil, first photo to apply the soldering paste. So no more duct tape anymore. Then you have the pick and place machine to just put your component on the soldering paste. And trust me, when you have like 64 LEDs, LEDs to place, it can be very useful. And we have the brand new reflow oven. I'm not sure you can cook pizza in this one. My boss didn't allow me to try.
Yes, you can, but
Jan, if you're
to
watching, please, for science. So for hardware, it works pretty much well. Okay. It's the result, the final version of the board. So smaller, of course. We have 64 GPIOs, like I said, with LID for each of the pin. You can connect a target working on the 3.3 or 5 volt. So we use a Cyclone 2 FPGA, USB 2 communication, like I said, and
you have protection against ESD discharge. It's important when you plug and unplug yours.
As you can see, it's not the size of a USB key, but you can hold it in one hand. Okay, here it's better. So it's pretty lightweight and fit in one hand. Okay. So how do we organize Hardsploit? So with Hardsploit, you can plug, wire your target to Hardsploit. You will be able to manage a list of components that you have created. So you can search components, create them, share them. You have the commands part. For a specific component, you will have commands. And then the interact module, where you can find the list of the buses we can interact with it. For the graphical interface, I use the Qt, well-known Qt library with Ruby programming language. And I divide it in 3 parts. So you have the chip management to manage your components, your electronic components. Then you have the wiring helper to help you wire your target to Hardsploit. And then you have the command manager to create commands, to edit them, classical. And it looks like this. So this is, for example, on the middle, the first window that opens when you launch Hardsploit. You can see that we have a table with several components. So the current chip we are using is 24LC64. When you work on a specific chip, it will appear in the tree you can see on the left. You have several options. The wiring helper, you can edit your component, of course, use it as a template to create another similar component. Delete, obviously. And under the manage option, you will have all the buses compatible with this component. So here, the component uses the bus I2C, the I2C bus. And you can add specific settings that we ask for this bus. You can use the custom commands menu. You can import and export. The export is like the dump of the content of the component. And on the right, it's the form to create a component. So we ask for the reference of the component. We ask for the voltage. We ask for the manufacturer, the type, the package. All the information required are, you can find them in the component datasheet. So nothing difficult. And the last part is the pin table. So we have like 8 pins for this component, and we only use pin number 5 and number 6. So we can see how they work on I2C, and we have the signal associated to this bus and to this pin. Okay, so the important part, it's the wiring helper. It's one of our favorite modules. It helps you connect your target to Hardsploit. And I'm colorblind, so I don't like to try to put the blue and the pink. No, we work by using LED. So here is the datasheet representation of the component. When you have created in Hardsploit, you can use the wiring helper module, and it gives you another representation of the component. And we can see that here we have the pin number 5 and 6. And if you want to wire the SDA, for example, you just have to click on it. And when you click on the pin, it will automatically turn on the LED, the specific LED on the board. And so you know where to connect this pin to Hardsploit.
Yes,
so,
here. For each pin, you have a LED to explain, to show where you need to put the wire. I don't know if you use Bus Pirate or something like that. Sometimes it's very boring to find the good wire, and sometimes you have a big joke. If you want to put, for example, SDA for E2C, you need to put your wire on MOSI, and you don't know why. So it's not easy sometimes.
We try to make this step really simple. Okay, I'm going to be quick on that because we are going to see that in the live demo. And yes, a word about the API. So you can use it freely, of course. If you don't want to use the graphical interface, of course, you are not obliged to. You can create your own if you want, and use the API with your own program. So it's really open, well documented, so don't hesitate. Okay, so what's already available for Hardsploit? We can work with parallel buses. We have the helping wiring. You can work with I2C memory, I2C bus. SPI, we are compatible with SWD for JTAG. And you can use 64 GPIOs for your convenience to do some bit banging, for example. So that's what we have for the moment. And what we want for the future, it's, for example, the component and command sharing platform. For software, we can find a website with a lot of exploits, for example, and you can download them and use them in tools like Metasploit. And I want the same for Hardsploit. That say you can download a component with his commands and integrate it to your Hardsploit. You will have a UART module, the parallel communication, but with multiplexed memory, I2C sniffing, SPI sniffing. We want to add wireless communication too for a training platform. Metasploit integration, of course. So just launch the Hardsploit module on Metasploit, and you will be able to use Hardsploit. So we are working on that. The JTAG pin-out finder, the one wire, the CAN bus, etc. The list goes on. And now, because a live demo is better than a speech, we are going to show you a concrete case of by using Hardsploit. So let's imagine we have a door that use an electronic lock system. So you have a pin code to enter, A, B, C, D, 4 letters. If the combination is right, the LED turn on, and if the combination is wrong, of course, the door stays closed. So what can we do? We open it, and we find that, okay. So we can see there is 4 buttons, A, B, C, D. And then the fingerprinting step. So we can see that we have 1 SPI memory, 2 I2C memories, and 1 microcontroller, okay. Online, offline analysis. Are we going to unsolder the component or just to plug wires directly on it? Your choice. And that's the scenario. We open Hardsploit, we create the component, we connect the component to Hardsploit, we enter the component settings, of course, and then we dump the content firmware, the content of the memories, and well, we will see what we can do with that. Okay, so first, we are going to work with the I2C bus.
Yes.
No, that's not Tor at all.
No, of course.
Okay, so we launch Hardsploit.
So the first step is fingerprint, of course, and trust me, on the board you have a memory. We start with E2C, and in fingerprint we found two memories. So when you know the E2C protocol, you need to know you have addresses, etc. So with E2C, just click on the memory, and you can use a function to scan the bus. And after that, we have a list with all available addresses. So it's very interesting because with just 2 clicks or something like that, you have information how many memory are available. Of course, you can see with your eyes on the board, but you need to go on the datasheet, etc., to find the good address, because the address for E2C is hard, and you need to put some wire with pull down or pull up for the guy who knows that. So it's easy to click. So for the demo, we set the setting to A2 and A3 because the sensitive data is in this memory. Trust me. And if you want to dump all the content, you need to read the datasheet to know all the size of the memories, where I need to read, etc., etc. Write the pointer. It's too complicated.
Not the case anymore. Yeah. Just double click on export, okay.
And choose. Yes, we can use the same.
Replace it, okay. So this is the dump.
Choose full dump.
Just click full export. Okay,
and it's finished. So just click on the file. Of course, I use Bless on Linux. Maybe you use another tool. It's not a problem for that. And now you can read all the contents. For the demo, it's lots
empty.
of FF. But if you
oh, what's that?
Of
course. Password.
Yeah.
Snap.
So it's true. In the real life, when I use some
hardware, it can happen.
It can happen. you can find some sensitive data like that. It's true. So here, of course, it's just 4char for the demo, and you can use it to open the door. We can try now, and the goal after is, for example, to change it and try again if you can change the password. We do that online.
Let's try to change the password.
So the first step is just to check if this password is a good password. So ACDB.
ACDB?
Yeah.
Okay. Can we please have like the...
Yeah.
Okay.
So I restart to be sure.
Yes.
A.
No.
Oh, no. It's not. Oh,
right.
So we start again.
Oh, no, still not.
Where is the board? Yeah. It's not easy. So password ACDB. ACDB. So of course we have. Wow. Of course, this demo is easy, but now we change the password and try again. So don't forget, you can remove the password and do some sort of denial of services. For example, if I put a char difference or ABCD, it's not possible to type this password.
To open the door.
You create a DDoS, sort of DDoS. No, it's not the goal today. So, to change the password, you can dump all the content, change with your preferred software, and you can put all the data inside the memory after. But you need to erase the content, etc., etc. So maybe we can just create a custom command to read the memory, for example, in your hardware hacking stuff. Or you can just change for share. When you create a custom command, you can just change the data. So, of course, we create a lot of command for demo or something like that. So, today we can change the password with, I don't know, BBCC. Or
BBCC?
Yeah, yes.
So, just so you know what a command looks like.
Yes.
So, it's a command, it's just a name, a description, and a list of bytes that you can see in this array. And all the commands of the components is in the datasheet, so I won't be long on that. And we want to change the password, so when the command is created, you just have to execute it. Okay, we see that
you receive ACK, because in
ACK.
C you can receive ACK, so it seems to be
so
okay.
Let's try to dump the content again.
Yes, to be sure. To be sure, we change the password, we read again, and check if the password changed.
Okay, replace. Full export. Okay.
Yes, it's not at the beginning.
Ooh, okay. So we can see that the password is changed. We can test it.
So the next step is to try if the password is right. So for that, we go again on the board and BBCC. So B, C. It's okay. Yeah. C.
Okay.
Okay. Of course. So the goal is just few commands or few click. You can create your own command. When you do some hardware hacking, you need to create a custom command most of the time, and it's very boring to create. You can create your own script. It's true, but here it's just few click. And I know all the people like a command line, but sometimes just 2 click, it's cool. I think.
Okay.
I think it's okay for HUC memories. So we can do a demo with SPI protocol. When you do some hardware hacking stuff, you need to know about HUC and you need to know about SPI, of course. So the next step, we will close all to be sure no problem. Okay. I replug another wire, so I don't know if it works the first time because I just put, but I think it's okay. The first step is the same. You check the wiring, to be sure all is okay. No here. Sorry. Yeah, the same. Of course, when you have 2 wires, it's easy to plug the wire. We have 5 wires. It's not complicated, not easy, but it's not complicated. So, to be sure, we just check if all is done. If you put, I don't know if you see.
Here we want to connect the CS pin to Hardsploit, so we click on it, and here you can see that we have to plug the CS pin on the first pin of Hardsploit.
It's also bottom and right.
Then you just have to repeat this operation for the 3 other pins, and it will be okay. It will be good.
Just check my ISO because I'm not sure.
Okay.
Okay, all this seems to be okay. Okay.
So now let's continue with the SPA. We have exactly the same commands. So let's try export. Okay, SPA replace full export. You can see that Hardsploit is processing behind. Okay, it tells you when it's over. Oh, another password.
Yeah.
at the beginning of the file this time.
So we can try if you want to be sure, but before we can change, it's the same things.
We assure you that it works.
So you can show just the command. I think it's interesting for SPI. Just if you have a flash or something like that, you need to send a write enable, and for that
that's a
just
specification.
Click here.
That's a specification of the component. You have to enable the writing before being able to write, of course. So first we enable. Okay.
Okay. The command is enabled.
So
now you can write on the memories.
6 is a byte to enable the writing.
Yes, you have this information on the data sheet.
And then we change the password. Okay, we see that we send 66. It's the B letter, the equivalent in hexadecimal of the B letter.
And to be sure, we read again.
Dump again.
The same things.
Okay, dump over. Okay.
So, perfect.
I2C, SPI. And
yeah. It's the same thing. You can try. The password, of course, is the same. And you can try your custom if you want to read, I don't know, 6 byte at 10, address 10, etc., etc. You can create your own command. It's very easy if you need to use it a lot of time. So it's very good for that. Okay, the next step.
We have a microcontroller, so we may be able to dump the firmware of the lock, of the electronic lock.
All people know SWD protocol or not? It's okay for all? Okay. It's like JTAG, but for ARM processor, okay? And with a custom protocol, very well documented.
So for the JTAG, the SWD, you don't need to create the component in Hardsploit. You just have a simple menu right here. And you have 4 options, that is detect, export, import, and erase. So first we want to detect if the wiring is okay. Yeah. And to do that, we just click on detect. So behind, we upload the SWD firmware inside the FPGA. Then we execute the detect command. And we can see that, well, we have some information.
Yes, for the moment, it's just the beginning of SWD module for Hardsploit. So for the moment, you have all the information of the target. And after that, you can map very easy to dump all the content. If you read the data sheet, you can read for this chip, you need just to use this address with this size. But the size, you can read the size of the flash directly inside the microcontroller, yes. So it's automatic tool because SWD protocol send good information to read all the content of the flash. So it's perfect. If you plug just detect to be sure all the wire is done, and after just import or export like dump. It's
okay,
easy.
Let's try the dump, for example. So same as usual, you select a file. log firmware.bin. Okay. So Hardsploit is processing. Okay. And okay, here we have the electronic lock firmware.
Of course, without readout protection for the expert. And if you read the content with readout protection, you read only 0 or FF is depend on the microcontroller. So most of the time, you can read the firmware like that. But with not easy tool like OpenOCD or something like that, it's a very good tool, and we need to have a framework with all tools inside the same, and it's for that we create Hardsploit like that.
We want an all-in-one tool.
One tool, 2-click for SPI, 2-click for E2C, 2-click for SWD. I'm expert on hardware hacking, and I need to not to lose my time, just to create a bridge between the hardware and the software. So now, with few minutes, it's possible to read all the content. So now I can focus on reverse engineering. Okay, it's for that we use this tool all the day.
Okay,
so we have a string at the bottom, of course, for serial communication or something like that. You can read all the content here. You can inject a backdoor or something like that if you want to re-put the firmware after. We have some checksum control sometime, but it's not security, so it's not a problem for that. So now we erase all the content of the firmware, and we read again, and we just put again the firmware to demonstrate. It's very easy to dump and to write again on the side or on the target with just a few clicks.
So we erase the content of.
Are you sure?
Yeah, I'm sure. Let's do that. Okay, it's over. So now, if you try to enter the password of the electronic lock, of course, it will not work.
Yes, we can.
Yeah.
If you can switch, just. Yeah. If I put on some button,
no more light.
No more light. Of course, the firmware is erased.
And now let's just import the firmware again. So
change maybe the firmware to keep. Change the name. Okay. Yes, you can take it. Yeah.
Okay. So Hardsploit is writing the firmware right now. Okay.
Okay.
Okay. Let's try to see if.
So okay. Now when I put the button, we have alive again. Okay. So it's perfect. The right work with just one button, one file, and 2 seconds. Okay.
So of course, you.
Yeah. Thank you.
You can have a lot of fun. Here is well-known router, Linksys router. Linksys use, for example, so you fingerprint, you open it, you fingerprint. We see that we have memory that is using the parallel bus, and so it's always the same thing. We unsolder it and we resolder it on our own PCB, or you can use custom
a board. Yes, because very a fine pitch and a very close, and most of the time it's not easy to just put a wire.
And if you can't create your own PCB, you can use this kind of device.
So I'm DIY enthusiast, and so I'm electronic engineer. It's not complicated for me to create the custom board, but sometimes for hobbyists or just to check, or I don't know, you can just use a socket without solder. Without solder. Yeah.
And now you understand why we have 64 GPIOs, because of course parallel bus need a lot of GPIOs.
And if you want to put this wire, you can use Hardsploit for each wire. And it's very interesting when you need to put about 60 or 64 bits.
So we were able to dump the content. It's the same process that we have seen before. So I think it was OpenWRT firmware.
Yeah, yeah.
That. So we are not going to remake the process, but it's exactly the same.
With the SquashFS, etc. Today it's not the reverse engineering talk, so it's for that we don't explain. It's not directly the firmware, of course. It's SquashFS, read-only.
It's a file system.
system.
So then you will have to remount it, but it's not the Hardsploit task for that.
Yeah, it's open firmware, so it's not very interesting to dump.
It was mainly for testing the parallel bus.
Just for demo.
Okay, I think we are over. And of course, if you want to learn more about our project and to follow us, you can go on the website. And if you have questions.
Any question? Yes. Thank you.
Yes, thank you again for that very interesting talk. The demo gods were with us, lots of live demo time. So are there questions in the audience?
Yes.
I see one over there. Please come to the microphone.
Just 64 bits of input, but can you also apply an external clock and actually have the input latch, for example, parallel bus, and actually latch it into the FPGA using this external clock, so you can get the maximum clock rate?
For parallel, we are in asynchronous mode, so it's not necessary to plug the clock. But if you want, you can just create a custom firmware, and you can use the clock of your system. But you need to send the clock, so you can generate the clock by FPGA. To be more simple, it's just asynchronous and just generate address, and it's works perfectly. But
what's the maximum clock rate you can sample on?
Sorry?
The maximum clock rate to sample it from with the clock domain from the FPGA.
You don't have a sample, but I can. It's not a sample; it's just a latency, and we have about 7 nanoseconds.
Oh.
Okay.
So please leave the room quietly if you really have to leave now. Otherwise, think about staying for a few more minutes. I guess there are some more interesting questions. I heard there's a question from the internet.
Yeah. Hi, I'm over here.
Oh, yes, thank you.
Can you say something about the difference between Hardsploit and maybe a common FPGA development kit like a Cyclone starter kit with an expansion board?
You have the same FPGA, so of course, if you put my firmware inside, it works with the same behavior, of course. But don't forget, you need to program your FPGA. So for that, you can use a blaster, for example, or external tool. So here, we use a microcontroller to program external memory, to program the bit stream, etc., etc. So we are create a big bridge between FPGA and graphical interfaces. So in fact, you have graphical interfaces, API in Ruby, communication with microcontroller, and microcontroller communicates with custom internal protocol with FPGA. And inside the FPGA, yes, you have 2 modules. We have Hardsploit core, and to create some communication with microcontroller, etc. And now we have a module. So if you need SPI, you just create SPI state machine, and you can fill a FIFO, first in, first out memory, and it's okay for you. After that, Hardsploit core do the process and process data, and all is done for you. So in fact, you have an array data, array on Ruby, and you have a FIFO on the VHDL. and you can do what you want. Okay, so it's true you can use the demo board, but you need to program, etc., etc.
Yeah, you will not have the full process, of course.
Yeah.
Okay, then next question over to the side.
Two questions first. I looked at the site, but didn't see any schematics, source codes, whatever. You will release them?
So, for the moment,
we are talking about it.
Yeah, yes.
We are not sure for the moment, but we are talking about it.
For the moment, graphical interfaces is open. If
API.
you don't use it, it's not a problem for you. But you can use API. Of course, API is open, and now you can use a very little line, Ruby line, to interact with SPI. For example, just create a Hardsploit object, and just the next line is dump. Okay? So today, you can use Hardsploit like that. Just 2 lines of Ruby code. For the schematic, for the moment, it's not open hardware. But maybe change.
We're not sure about that. Yeah.
Okay, second question. Such a project lives by a community, because you probably cannot go and implement all kind of protocols and chips
Yes.
and set it up.
Yes,
but
of course. And the goal of Hardsploit is to create a database like Metasploit. And you see, we have only 5. It's not true. We have more than like. It's just for the demo. But we have a problem, because if you are an expert, it's not complicated for you to create a command and target. And another people can use it just like that with 2 clicks, of course. But in real life, it's just 2 clicks because you need to create. And the next step is to create a community to create a command. But it's not enough. It's true. We need to create another module. And it's for that we try to change the schematic license, etc., to, I hope, answer your question for the community.
We will rely a lot on the community to share their components they have created or their commands. So someone that don't know how to interact with a specific component, he may find the component online, download it, and add it to his Hardsploit, and he will have nothing to do that just clicking.
Okay. So
at the beginning, Hardsploit is for internal purpose, and now I think you are here, so it seems to be you are interesting by Hardsploit. So maybe we can change. It's
still in development, of course, and we are thinking the way to adopt. And
yes, because we use Hardsploit all day, so I think we can increase the compatibility of Hardsploit with you.
Okay, then next question. Again, another question from the internet. The internet has no sound.
Yeah, no. Can you think of known limitations to Hardsploit? So will there be any components or protocols that will never be supported or can never be supported?
The limit is the same answer. It's 7 nanosecond latency. And after that, you can create what you want. Not exactly. You have a problem with internal memory of Cyclone 2. So it's complicated to answer your question, because the goal of Hardsploit is to create a framework and versatile framework. And of course, the limit is only 7 nanosecond latency, because we work 150 megahertz, and is
for the bus we want today, we are not limited by the FPGA. So
just with this feature, this limitation, just 7 nanoseconds, yes.
Okay, thanks.
Then next question from in here.
Yeah, I think the time-consuming thing will be getting the data sheet and modeling the chip. And I think it's a great idea to have a sharing platform for this.
Yeah,
But
yes.
intermediate step, how far are you? What is your internal database that you have right now that you, when you get it right now to the market from the first step without having the sharing platform?
Okay, what we give in the database when someone gets the product? That's what you...
Yes.
Oh,
yes.
well, the component we have worked on, I think, and the one you can... we are going to give a component for each bus so that, and commands so that people have, can take example on those components to adapt to their own component if they are not using the same.
And don't forget, for example, the button full dump, full export, etc. It's automatic. And you need just to specify the size of your memory and all is automatic. So if you want to dump 64 kilo memories or 32, etc., it's the same, just change the size. And the size is on the title of your datasheet. So for example, for SPI or E2C, it's not a problem to have a custom command because you don't need. Okay?
Yeah, so maybe it would be a good idea to have an inherit command to take the chips you already have and just change them and have another one.
Yes, you can use the existing component as a template to create another one. Yeah.
Okay, I think we have time for 2 more questions, perhaps. Please.
Will you be able to do detection of JTAG and serial on if you don't know which points on the board?
Yes, it's for that. So for JTAG or SWD, most of the time you have on the top or on the board SWD and TMS, etc., etc. So it's true. In this example, we know the card, so it's easy. It's just the beginning of SWD. It's for that. It's not very clear for SWD, but in fact we have only 2 wires. And you can read the data sheet, and you can find a clock of SWD and just use a multimeter to find the pin on the board. And for Hardsploit, we add the buses next week to use with helping wiring.
The question was, how do you connect the SWD to Hardsploit or to the target?
No, I was just wondering whether you'll have the same functionality as JTagulator has now, where it will... You connect it to lots of points, and it will attempt to identify which points are JTAG or serial.
I'm not sure I understand.
So say you have a board with no labels, and you're trying to find where is the serial interface, or where is the which are the JTAG pins, and JTagulator will try to...
Oh, yeah, yes, yes. It's not a brute force for the moment. Yes, I understand. So for the moment, you need to put in the right way, the right wire. If not, it doesn't work, of course. But it's FPGA, and you can create an algorithm to brute force like JTagulator. Yeah. If you go on hardsploit.io, for the next step, is the first step.
We are going to implement this functionality. So you will be able to connect the wire and just launch the detection. Mm-hmm. Okay. So it's on its way. And
you can replace JTagulator with this tool, but it's not the goal of Hardsploit. It's just to have a framework, because we love this tool. It's the beginning of hardware hacking, but we want to put all the good tools inside the same, and the community you can use it easy. Yeah.
Okay. Thanks.
Thank you.
So thanks again for the questions. The speakers will perhaps be outside in a minute for further questions. But I think we can all give you a warm applause. Thank you for your talk.
Thank you for listening.